check. 1, 2, 3. So this is the citation for M605, right? The yes, this is one of the last by the we have to share the screen to us. Yes, the radius expression for atomic radius, and we need to share. Sure. Yes, the radius expression is for atomic radius, and then we need to sure. All right. Okay. The screen is right. Yes. Right here we alive at the atomic radius, right, which is presented by gold, right? And then there is something wrong. Yes. Oh. Okay. You know that this is the expression. Oh, yeah. First, we have to be clear about this table, right? The speed number, which is a kind of quantum number, is the unit of speed is h/, here, right? You have ever seen the h/, before? h slash is the one is expressed in this one. You can see here in equation 32. I don't know whether anyone would like to join in Zoom or not. Right. นภัสนะครับนภัสอยู่ที่ YouTube นะครับคนนะครับ and where's let me see whether one join. There is no live version for this one. Let me zoom channel. Anyway, we go here. Yeah, h slash is h divided by 2 pi. This one, right? It's reduced Planck constant, right? It's you start from 6.6 times 10 to 34 Joule second, and you just multiply it in terms of circumference, right? The distance around the circle. And pi is 3.14, and this term is something about 6.28, and you just divide. It's gonna remain 1.0 blah 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 and times into SCI33206, the same order, and the unit is the same, right? Because 2 pi has no unit. Yeah, H slash is the reduce the Planck constant, and that's the Streamlabs2YouTube. Oh. All right. Okay. You have to use this one. Check the microphone right now. Check 1, 2, 3. Check 1, 2, 3. Check 1, 2, 3. Okay. This is the section for M604, right? The screen is alright, and yes, right here we arrive at the atomic radius, right, which is presented by the bow, right, mean bow. And if there is something wrong, yes, oh, okay, and you know that this is the expression. Oh, yeah. First, we have to be clear about this table, right? And as you know, the spin number, which is a kind of quantum number, is the unit of the spin is h/ here, right? You have ever seen the h/ before? h/ is this one, is expressed in this one. You can see here in equation 32. I don't know whether anyone would like to join in Zoom or not. Right. นภัสนะครับนภัสอยู่ที่ YouTube นะครับ1 คนนะครับ and who else? Let me see whether anyone want to join. There is no live version for this one, right? In Zoom channel. Anyway, we go here. Yeah, h/ is h divided by 2 pi. This one, right? It's the reduced Planck constant, right? It's you start from 6.6 times 10 to 34 Joule second, and you just multiply it in terms of circumference, right? The distance around the circle, and pi is 3.14, and this term is something about 6.28, and you just divide. It's gonna remain 1.0 blah blah blah, and times 10 to negative 34, the same order, and the unit is the same, right? Because 2 pi has no unit. Yeah, h/ is the reduced Planck constant, and that's the unit of the spin number. And you know that once we say it's the spin number is 1/2, it means you have to multiply it by 1.05 Joule second. So it was times 10 to negative 34 Joule second, and that's the spin number, the total value of the spin number. But for simplicity, we would use quite often only 1/2. Okay, and all these 3 subatomic particles would have the spin number as 1/2, 1/2, 1/2. Okay, the result from this table, the table number 3, could be summarized as the following text. The number of protons in an atom is unique. Okay, this is quite important, and that's the location here. Okay, if you change this number, you're gonna have the different elements in the periodic table. The number of proton in the nucleus of the atom is equal to the atomic number, which is denoted by Z. Okay, and Z is, it's integer, is a kind of integer. ถ้าแจ้งเพื่อนนะครับฟิสิกส์นะเดี๋ยวผม คือผมก็เพิ่งลืมบอกไปนะครับเพิ่งพิมพ์เมื่อคืนนะครับโอเคผมก็ลืมแจ้งคุณนะครับก็เลยไม่ได้ยุ่งกับอย่างอื่นนะครับต้องขอประทานอภัยด้วยนะครับโอเคyeah the atomic number is denoted by Z and the in a neutron atom the number of electrons is equal to the number of protons and that's the stable right the number of positive charges is equal to the number of negative charges right and yeah that's the stable condition and once you remove the electron from an atom okay you're gonna have something which is not balanced and yeah that's the ionization state right yeah that's a different story the mass number of the atom which is denoted by M okay the capital M is equal to the summation of the number of protons and neutrons in the nucleus locates there okay M is above and Z is lower okay on the left side of this letter okay a hydrogen-like atom is an ionized atom that occupies only one electron okay it means that if you have something bigger than hydrogen for example helium has the 2 protons right and if you throw away one electron from the orbits of helium you're gonna have the same kind of atom as the hydrogen okay and that's the meaning of this sentence when an atom has an atomic number set 1 2 blah 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 and 3 so on the term E square is denoted by Z E square so what does that mean for whatever you have whether you have the radius okay E square is gonna replace it by Z E square okay whether the radius or the energy the 3 energies with its the potential energy which is these where is that here the potential energy if you have E square you just replace it by Z E square okay the potential energy the total energy or the kinetic energy if you have E square just replace it by Z E square it's gonna be the same thing okay and that's the condition when you throw away a few electrons from their orbits where is that okay so for example if we have the simple expression of minus 13.6 which is the conventional expression where is that โอ้รูดเมาส์ไม่ค่อยสะดวกเลยนะครับ okay the here the Balmer I don't know it's Bow expression right here if you have En which is equal to 13.6 in divided by n square that's the expression for the hydrogen atom right and เดี๋ยวผมขอมอนิเตอร์ที่เครื่องก่อนนะครับเพราะว่าเดี๋ยวมันเกิดเน็ตล่มอะไรขึ้นมานะครับ this term. Oh, sorry. Swinapat. Okay. And yes, so this one, right? This is zoom, okay, only Kitipan is there. Okay, only Kitipan is here. And where's okay, เรียบร้อยครับ yes once we start from equation number 27, which is the typical Bohr expression for the hydrogen atom, we need to extend these term for to cope with the bigger atom like helium, but you have to throw away a single electron from the helium atom, or you have something like lithium or something like that, which is bigger than helium, the next element, right? Yeah, you have to throw away 2 electrons for the helium atom, or for the lithium atom. Periodic table. Okay, periodic table. Okay, periodic. Okay, let me bring you to the periodic table, right? This one. Yes, if you take a look at the periodic table, the first atom, the smallest one, is the hydrogen, right? Which is at this location, and you can see the atomic number, or the letter Z is number 1. The number of proton is 1, and the next element is helium, right? And yeah, the number of protons in the nucleus is 2, and you have 2 electrons, right? But in order to use that expression, you have to throw away a single electron from the orbit of helium. For the next one is the lithium. If you want to use that expression, lithium has the number of protons inside the nucleus as the number 3, right? There are 3 protons. You have to throw away 2 electrons from the orbits of the lithium. You're gonna get the same expression like a hydrogen. It's called hydrogen-like atom. Okay, the atom that has similar structure to hydrogen. Okay, and the next one is the beryllium, right? If you want to use the same expression developed by Niels Bohr, you have to throw away 3 electrons. Okay, so that the remaining number of remaining electrons is only 1, a single electron. Okay, and that's the way to cope with these new expression, equation 51. So what is inside equation 51? The energy at the end orbit, which is somehow like this. For the electron inside a bigger atom, it's called hydrogen-like atom. It's gonna be minus, okay, the same thing, negative 13.6 times Z square. Okay, Z square, Z is the number 1, 2, 3, right? If your Z is number 1, it means you use this expression to the hydrogen atom. But if you use or substitute Z by number 2, you're gonna have the expression for lithium, right? The second element on the helium, the second element in on the periodic table here. Okay, next one If you use Z as number 3, okay, it means you are talking about the lithium atom, okay? And if you use Z as number 4, okay, 1, 2, 3, 4, 4, you are using that formula for beryllium, which is this element, okay, and so on, like the boron, carbon, nitrogen, oxygen. This one I forget about it, and neon, okay, and yeah, yes, the expression just have Z squared, the atomic number, at the numerator here above 8 square, okay, at the numerator, and the unit is the EV, okay. Please note that it's not joule second, it's only EV. All right, there are only 2 channels in the YouTube, and anyone who would like to join in Zoom, just let me know, okay. ใครต้องการเข้ามาที่ Zoom ก็แจ้งผมนะครับ แต่ว่าหลักๆก็คือมี2 channel เนื่องจากว่า OBS ไม่ได้สตรีมนะครับเนื่องจากคอมพิวเตอร์ใช้รันงานวิจัยอยู่นะครับเลยไม่อยากรบกวนเขามากนะครับโอเคyes so let's go further. You know that the energy level has been modified to this one, right, which is the result from 27. And for the Littback formula, this is the Bohr expression for energy level. We have more general expression for any atom which is bigger than hydrogen. The next one is the Littback condition, right? We start from the Littback condition in 31. It's 1 by lambda, and the Littback constant 1 by nf, the final state of the electron orbit, square, minus 1 by ni square, which is the initial orbit, right? You get the Littback constant, that's 1.09 times 10 to 7, and the unit is 1 by meter. But for the Littback form, because this expression actually is derived from here, right? Littback condition is this one, and you know that E square appears here, right? E square appear here, but E square times E square, so that we get E to 4, right? To the 4. E with the power of 4 means E square 2 times. So as we know, Z square, E square is is replaced by Z E square. So once we have E to 4, it should be Z square and E4, right? So yeah, that's why we have here Z square appears at after the Littback constant, and the remaining thing will be the same, which is 1 by nf square minus 1 by ni square, 1 by lambda. And the next one is the next quantity is the radius of the atom, okay. And you know, before the table number 3, there is an expression for the radius here, which is developed by Bohr again. In is 0.05293 n square, right? And the unit is nanometer. And once you go back to the original expression before you make the substitution of several constants, you could see E square at the denominator here, right? Whether with h/expression or the typical h, the Planck constant. You have the E square at the numerator. So, and according to our rule, wherever you see E square, you have to replace it by Z E square. So that's why we would have Z here at the denominator. And yes, that's the case here. You have Z at the denominator for the radius, and that's the Bohr atomic radius. But this one could be applied to the bigger atom like helium, lithium, beryllium, boron, carbon, nitrogen, and I forget the F, the night, nine elements. F, what is that? Fluorine. Okay, fluoride. Yeah. Yes, that's the nine elements on the periodic table. You know, I'm from electrical engineering. I live every day. With electricity, so I would not have so much chance to look at the periodic table quite often. So that's why I sometimes forget the fluorine. Okay, the fluoride. Okay, let's get back to our lecture. Yeah, you have three expressions for three quantities: the energy level, the wavelength expression, and the radius of the atom. Okay, there are three quantities that could cope with the bigger atom. Okay, now we arrive at the first example about the bigger elements, right? For the bigger elements, we consider the helium. Okay, helium here. Let's get back to the to the table. You have here helium, which is the second element in the periodic table, right? And as you know, helium has two protons, two electrons, right? And once they say H with plus, okay, H with plus, it means the ionization version of the helium. Okay, because we have helium plus, we have helium and plus. It means one electron. One electron is missing. Okay, one electron is away from the helium atom. And once we say helium 2 plus, it means that two electron missing. Okay, this is S and this is R, right? Missing. So yeah, it means this is a proton, right? Proton of the helium, and you have two electron moving around the nucleus of helium, and you have another electron also moving around the nucleus of the helium. But we throw away, we use any kind of energy like electric energy or magnetic energy, magnetic force or electric force, and whatever you throw away, you move it out of the original orbit. So you would have only a single electron, and that's the condition. We could apply this formula, right? En minus 13.6 z squared by n squared. That's the energy level. Okay, denoted by M. The helium, the ionized helium, has an electron in orbit denoted by N equal 1. When the atom is in its ground state, okay, it corresponds to N equal 1, and that's the quantum number as number 1. Find the energy in the ground state in electron volts. That's this expression, right? 51. And find the radius of the ground state orbit So they asked us about this one. Okay, the two quantities only, 51 and 53, right? Yeah, let's start our computation. What is that? They want this one, right? The helium, right? National helium has two proton, right? Helium has two proton, but has two proton, two electron. Expression of 51, right? En, okay, equals to approximation minus 13.6 and z square divided by n square. And you know that we have to substitute z by 2 because this is the helium atom. It has two protons, which correspond to the atomic number as number 2, and in the ground state is going to be the number 1, right? Yes, and yeah, let's substitute everything there, and then you use the minus 13.6 and 2 square divided by number 1 square. Yeah. You just compute it, right? It's gonna be 13.6 times 4, right? Yeah, 54.4. So it's gonna be 54.4, and the unit is not joule, right? It's electron volt, and that's the first answer we could deliver, right? Let's check with us. Yeah. Oh, sorry for that. It's negative 2. Okay, minus 54.4 electron volt. And let's move to the second quantity, which is the radius. N equal to 0.0523 divided by z times n square above, okay, at the numerator. And of course, it's in the same way, we have to replace the atomic number by 2, right? Because this is the helium atom, and from the original table, it corresponds to z. Here, z equal to 2, right, which is the helium atom, right? So z is number 2, and we consider ground state, okay? Not only the detail of the which atom, right? Which orbit you are considering is also important, right? This one, n equal to 1, because we want to say something about the ground state. So it's 0.05293 in number 1 square divided by 2. So that's the number we're gonna put into the calculator, right? 5293. .0293, right? I'm not sure that it's correct. Let me see. Yeah. 5293 divided by z, which is number 2, right? Divided by 2. 2026465. 0 to I forget, my brain is not good. 26465 26465, and the radius is in nanometer, right? This one, and yeah, you can see that it's around 0.2 or 0.8 angstrom, right? Which is Tesla's to -10, and that's the angstrom scale, right? And as I told you earlier, the atomic size is the scale of angstrom, which is 10 to the -10. Yeah, and that's the case for the for 53, right? The radius, right? Yeah. So let's talk about lithium. I didn't write that down. The solution to this one, right? Okay, let's consider the doubly ionized lithium. Doubly means we throw away 2 electrons for the lithium. Let's get back to the periodic table and let's find where the lithium located. Okay. We start from helium. That's a single. That's the atom with single proton, single neutron, electron. The helium with 2 protons and 2 electrons. The next one is lithium. Lithium is right here. Okay, lithium has three protons and 3 electrons. Right? So when they say three doubly ionized, it means that we throw away 2 electrons from the lithium atom, the stable lithium atom. Okay, the stable atom would have the number of protons as the equal to the number of electrons, right? So, but in the ionized state, we throw away electron, and in this case, doubly ionized. Double ionization means we throw away 2 electrons from the original atom of the lithium. So it means we are gonna have only 1 remaining electron in the orbit of the lithium. The nucleus is bigger, but still we have a single electron around the nucleus, and that's the double ionization of the ionized. In this case, is excited to the state. The electron is excited to it seizes somehow the energy and moves to the upper level in where is that? So you have here proton, you have here another proton, and that's the nucleus of lithium. And you have one thing is that you have a single electron around the nucleus of lithium. This is the lithium plus, and as I told you, 2 plus means we throw away 2 electrons from the original atom. Okay, so that's why we have 2 plus, because actually the stable lithium have 3 electrons. So, right. Yeah. What that means? First stage, the first excited stage. It means that this is the graph state. The graph state, and n equal 1, right? And here is n equal to 2, and this is the first excited state. Okay, and that's the meaning. And that means that when we are saying the first excited state, it doesn't mean n equal to 1. Okay, we say ground is the first one. Okay, ground is the first one. The first excited state, which is this is the non-normal state. Okay, it's equal to n equal to 2, right? It's excited. The higher level, higher state from the ground state. Okay, that's called first excited state. Find the energy, in the first excited state electrons, it is the unit BB, and here is the and here is the layers, right? Again, of the first excited state. Okay, first excited in equal to 2. Okay. Let's make a computation. So what we have to keep in mind in this scenario that we are talking about the lithium 2 plus, which provide electrons to a electron thrown away. Okay, missing. You can say that. Yeah. First excited state. First excited state means we have A equal to 2. Okay, and lithium atom means Z equal to what? Which number? Okay, lithium is over here. It means the atomic number is 3. Okay, we have Z equal to 3, and let's get into the detail. They want to know if the states E in equal minus 13.6 Z square divided by n square. Okay, and that's negative 13.6, and we have to substitute Z by 3 and by 2, so Z is 3 square 293, and Z times n square, right? And of course, in the same manner, we are going to replace the Z by 3 and by 2, and yes, 0.05293, and n is number 2 square, right? Divided by Z, which is number 3. Yeah, let's compare it in calculator. ไม่ทราบว่าคุณเอาเครื่องคิดเลขเข้าห้องสอบมีปัญหากันหรือเปล่าครับถ้ามีปัญหาก็แจ้งผมนะเขาไม่ให้คุณเข้าหรืออะไรอย่างเงี้ยแปลว่าคุณถอดรูทยากๆคุณไม่สามารถถอดด้วยมือและในเวลาที่จำกัดผมคิดว่ามันไม่เหมาะสมที่จะไม่ให้คุณมีเครื่องคิดเลขในมือนะครับในการสอนครับโอเค 0.05 เดี๋ยวมีคนไหนจะเข้าที่ซูมหรือเปล่าเลยแจ้งผมนะโอเค no one 0.0293 times 2 square divided by 3, right? So it's gonna be mean, okay, of course the radius could not be negative. It's 0.00573 radius and the unit of nanometer. All right, and that's the case here. Radius in nanometer. All right. Yeah. And now we arrive at the standard model of elementary particles. We're gonna visit these. We're gonna visit this table quite often. Okay. And I will say that this table is not finished yet, actually, because there might be some particles happened in the physics could find. All right. Yeah. Yes. How could we start? Okay. How could we start this one? ไม่เสียงมันดังครับดังเกินวันyeah okay we might visit this paper quite often and let's start with that there are in many ways okay if you take the view this is the fermion, right? As I told you, this is the boson part. Okay, there are two main parts. Fermion and boson. Okay, boson is something. I don't know. Something is still missing here. Okay, they might find something more in this side. Okay, because this is the current state. Okay, I could not. Maybe I would dive down for my life. I mean, not last until they would find something more. Okay, boson. Okay, boson comes from the word bose. It's the surname of physics. Fermion is the surname of the physics too. Fermions or something like that. I forget about why they call me Fermion. ที่แล้วยังแม่นๆอยู่เลยครับแต่พอไม่ได้สาระ Fermion comes from I think it's yeah in the standard model from Fermi, yeah. Fermi is a famous physicist. Okay, his full name is this one. Okay, I would bring you. Oh no, bring you to first person Fermion. Enrico Fermi. Okay, this is the famous. Oh no, this is German. Famous physicist. Okay, here this person, Enrico Fermi. Okay, lives in Italy. Yeah, he makes a contribution in quantum physics. Okay, and another person is Bose or something like that. No, physics. This person, yeah, Bose. Bose. He's an Indian guy. Okay, Indian physicist. Yeah. Boson comes from Bose. This person. He's quite intelligent. He studied only in India, and he found some physics in the same generation and Einstein. And he submitted his experimental result on his idea to famous journal of physics at that time, but it was rejected. Okay, his work is not accepted. Was not accepted at that time, and then he submitted he tried to contact Albert Einstein. To talk with Einstein and something like that. And Einstein has found that Einstein found that his idea is already good. Okay, so Einstein and Bose asked Einstein whether they could write the word to the famous journal, the famous physics journal. Okay, and yeah, it's Einstein agrees that, and why they say something to physics journal, it was successful. Okay, and after that, that's the beginning stage of professor. I invited professor to work in Europe and so on, and I think Marie Curie too. Okay, has invited me to work with. Okay, and that's the origin why we say boson. Okay, boson comes from the surname Boson, and fermion comes from the name Fermi. Okay, Fermi, sorry. Enrico Fermi, famous from Italy. Okay, he's Italian. And yeah. There are two parts of fermion. Okay, which is widely operated. These parts, the left hand side here, is called fermion, and from this side, it's called boson. Okay, it's called boson. And inside of the fermion table, we have elementary fermions, okay, and this is anti-fermions, okay. In the first row of the elementary fermions, we have the light one, which is called anti-up, okay. You have U, which is aqua. You have bar, which is the anti-version of up. This one is the mass of the aqua and anti-aqua are the same. You can see here 2.2 make electron property square. And the charge is different, and that's the point. Why we say anti-particle? Because it has different. The opposite side of the charge is negative 1 here, negative 2 by 3 of 1.36 times into 19 coulomb, right? That's the elementary charge by electron, right? But this is only by 3. And for the number, they have the same spin number, 1 by 2, okay? And for the charge 1, it has there is an anti-particle which is called anti-charm. You could see that the mass of the charm fermion is 1.28, and here is the same 1.28 for the mass of anti-charm. The difference is only the charm value, which is 2 by 3 for the charm quark, and minus 2 by 3 for the anti-charm. Okay, the spin number is the same, 1 by 2. Okay, and what about top? Sorry for that. I forget to. โอ้จะจบชั่วโมงแล้วผมลืมเปิดไฟให้ครับแล้วจะจนแจ้งเลยวันนี้เราจะลงรายละเอียดของstandard elementary model นะครับอันนี้คือโมเดลนะครับที่คิดค้นไว้นะครับเป็นif study chemistry you have pretty table right like this one. Hold on, this one. You have elementary table. That's the main thing for chemists, right? People working in chemistry. But for us, once you leave, you work physics. This is our table, the main table for us. This is the elementary table for particle, right? In physics. Okay. This is for physics. This is for. Oh, I'm sorry. This is for chemistry. This is the table for chemistry to people working in chemistry. And here for us, the table for people working in physics. Okay. Let's get further into it. Yeah. The top quark has the mass of 173 giga electron volt by c square. And it's denoted by the same way here, the letter P, but has R because we need to differentiate it from the top part. This is the end top. It has a shadow minus 2 by 3. Alright, and then that is the anti-particle for the top quark. And for the down quark is a little bigger than up quark. What is the difference? Not only the mass, okay, down quark has more mass and up quark, but also the shadow. The shadow of down quark is different. It's not positive 2 by 3. You could see here. It's not positive 2 by 3. This is negative 1 by 3. And that's the main thing about the down quark. Okay, and the spin number is the same. Okay, spin property is 1 by 2 of the S slash. The spin number is H slash. And the next thing is the strange quark. Now we have a bigger element. Strange quark has 96 mechanical volts each man. That's the man for strange quark. The shot is the same, minus 1 by 3, and spin number is 1 by 2. You could see that here that in this table, in these 3 elementary particles, they all have the shot as negative 1 by 3. These 3 elementary particles have the shot of 2 by 3, and here you have the anti-particles which has the opposite charge to that. It's minus 2 by 3, and here you have negative 1 by 3, and of course you could guess that the opposite way to negative 1 by 3 is positive 1 by 3, and that's why we have the anti-down quark, anti-strange quark, anti-bottom quark, which have the shadow 1 by 3, okay. So in summary, negative charge, positive charge, okay, the anti or the reverse version. Positive charge, you have negative charge here, and that's the quarks, okay. Even if quarks, okay, it's difficult to detect it, okay. Let's get into the leptons. Okay, leptons is what you may have already get used to because you know electron, right? You have ever heard electron before. Okay, electron is a kind of lepton, and physicists have found something like electron. It's called here in the forward way, it's called muon. Okay, muon is denoted by the letter mu. Muon is bigger than electron. You could see the mass of muon is 105. Most of these particles are not stable. Okay, the stable particle would be only electron. Okay, and muon is a bigger particle. It behaves like electron, but it's bigger. Okay, the mass of muon is 105. Okay, you could see it here, 0.51 mega electron. Well, this is 100. It's now 200 bigger in size than electron, muon. Okay, but the charge of electron, of course, you know that the charge of electron it's negative charge, right? Electron, and the unit is minus 1 because it's 1.6 times 10 raised to negative 19 coulomb, right? Again, the muon, which is bigger version of electron, has the same charge value, which is negative 1. If you want to get it in terms of SI scale in coulomb, you have to multiply this value minus 1 by 1.6 times 10 to negative 19. Okay, you're gonna get the quantity in coulomb. And not only muon, the bigger particle than muon is known tau lepton. Okay, tau lepton has the mass of 1.77 giga electron volt. Okay, bigger than mega electron volt. Okay, this is like 1,007, let's say 776 mega electron volt. This is 1,000. This is only 100. So this one is bigger version than muon, or even bigger than electron. Okay. So but please note that the chart of tau lepton is the same. Okay, spin number. And let's move to the next one, to the right hand side. We're gonna have here the antiparticle section, and you know electron is negative, is negative particle. It has negative charge, and you know that the physicists have found something similar to electron, but its charge is positive, not negative, like the electron. It's called positron. Okay, you know posit, right? Posit means positive. Okay, or positivity or something like that. So positron just follow from the word positive or something like that. Okay, it means it's like electron. The mass is the same as electron, 0.511 mega electron volt per square. The spin number is the same, 1/2, but the charge of positron is not negative. The charge of the positron is positive. Okay, unlike electron has the charge of -1. Positron has the charge of +1, and of course, corresponding to the muon is a big version of the electron. It has the same charge as electron. It has the same spin number as electron. It's called anti-muon. Okay, this is the anti-particle of muon. It has the same mass of muon. It has the same positive charge as positron, or it's the reverse version charge, or reverse charge version of muon. -1 here we have +1. And the spin number is not 1/2, it's 1/2 too, right? It's 1/2. And tau has also its own antiparticle. It has the same mass, but it has different charge. Okay, the opposite charge, which is +1. The spin number is the same. Okay, it's called tau, and bar is called anti-tau. Okay, the bigger version of electron, maybe you have, some of you may have ever heard. It's called electron neutrino. Okay, electron neutrino. Let's get into detail of electron neutrino. It's denoted by new with E, and electron neutrino. What is that? It's a kind of particle. It's a kind of particle. It has no charge. Okay, there's no charge. You could see here. The charge value is 0. The spin number is 1/2. And please note that this one is very small. Could see here electron has the mass of on the scale of mega electron volt. This one has the mass of electron volt. Simply electron volt without anything to make into or anything. Okay, less than 2.2 electron volt. Before the physicists believed that electron neutrino has no mass at all, but not the case. Someone argued that the electron neutrino has a very mass, but very small, slightly detected. You could see here the physics. You cannot find the exact value of the mass of electron neutrino yet. That's why they say less than 2.2 eV per second. Okay, because it's very light, very small. Is at the current state, okay, until at the moment we are living, human could not give enough information wise to detect the mass of electron neutrino. Okay, and let's get to the big version. Muon has also a zero sharp version, which is called muon neutrino. Okay, muon neutrino has no charge. Okay, it corresponds to muon, but it has no charge. But the mass of the muon neutrino is very small, less than muon. It is a little bigger than the electron neutrino, but still physics could not change the mass of muon neutrino. Yes, at the moment, maybe in the next 30 years or 40 years and so on, they could find the value of muon neutrino. Okay, the next one is tau neutrino. You know tau is big version of muon and electron. But the zero charge version of tau is called tau neutrino, and the charge value is 0. The spin number is 1/2. And yes, of course, once you have electron muon tau, electron neutrino, muon neutrino, tau neutrino, there will be of course the anti-version, and it's called tau it's called electron and anti-neutrino. The opposite version of this one, okay, of course, it's not like electron proton. Electron has no charge, so proton has the opposite way of charge, which is positive one. But here we start from electron neutrino that has no charge at all. It's charge 0. Electron and neutrino has also no charge, but the mass is the same. Okay? The mass seems to be the same. Spin number is the same. We will see electron and neutrino later. We will see electron neutrino later in physics nuclear. Okay. And for the muon neutrino, we have also muon anti-neutrino. For the tau neutrino, we have the tau anti-neutrino, and it's 19.2 mega electron volt per square. 19.2 mega electron volt per square. Okay. That's called tau neutrino. Okay. That's all about fermions. Okay. Fermions come from the surname of Enrico family. Okay. Italian guy, this person, Enrico family. This guy. Fermion come from his surname family. All right, guys. Let's talk about. Let's move to the right hand side. Boson. Okay, boson. Of course, as I told you, comes from the word Bose. The first name this guy. He's from India. Satyendra Nath Bose. Okay. He was born in 19 or 18, and once time goes by, that's already right. Okay, the boson. Okay, boson is not so complicated as the fermion. Okay, boson could be classified into two types, roughly speaking. The first one is called stellar boson. This is what the world has just found, Higgs boson. Okay, Higgs come from the surname of this species. Higgs boson. John Higgs. Okay. No. Higgs boson. Yeah. Oh no. This is Higgs boson. The word Higgs comes from Professor Peter Higgs. Okay, Peter Higgs. Higgs boson was discovered by Peter Higgs from England. Actually, Peter Higgs. Yeah. This person. Okay. Peter Higgs from England. Okay, he works in Switzerland about he works in CERN, okay, CERN in CERN, which is the lab the biggest lab in the world about electron particles.